Okay. So good morning. Is everything okay? Can you hear me?
Yes, we can hear.
Okay,
Yes, we can.
so it's working. So we were studying the compact operators, and our aim is to reach this eigenvalue, eigenvector decomposition. So we want to give a meaning to the, well, there are several things, but essentially one of the ideas is that for finite dimensional cases where we are analyzing matrices, well, we know that the notion of determinant and the notion of eigenvalue, eigenvectors is one of the basic tools. So A, let's say x equal to lambda x. So where A is now a matrix in square matrix. Okay, so, and we were studying yesterday the Freedom alternative, which is the fundamental tool Freedom alternative. So, and we are studying, what we are studying here is, okay, up to the fact that here we have lambda. If we take lambda equal to 1, which is just a scaling, you have to study essentially the operator identity minus A. So that T is a compact operator, so which is maps E into itself like square matrices. Then there are 4 parts. So the kernel of identity minus T is finite dimensional. The range of identity minus T is closed. And, well, this holds in general. The range of identity minus T is the kernel of identity minus the adjoint or perpendicular. And this is a general relation. C, if the kernel of identity minus T is equal to 0, it's equivalent to the range of identity minus T is equal to the whole space. And D, the dimension of the kernel of identity minus T is equal to the dimension of the kernel of identity minus T star. Okay? So yesterday we saw the first part, and well, we will see that the other parts, they are really related to the eigenvalue problem. So let's go on with the proof. So we have seen point A, and point A was yesterday. Then we have point B, and point B we have only to prove that the range is closed. Because we have seen that as a general fact, the orthogonal of the kernel of identity minus T star is the range, the closure of the range. And just a comment, we have seen that the other relation, so that the orthogonal of identity minus T contains the closure of the range of the adjoint. And okay, in the case the range is closed, it coincides. But we will not do that because Okay, it requires some additional things, and time is what it is. So we have to prove so that is closed. So let, okay, now in the book it follows, okay, let's follow the line of the book just to easy the thing. I suggest you to show, I don't know if in the exercise I did not check, but one can show E over the kernel and a lot of steps, and the steps below are simplified. Okay, this is a comment. If you want to do that, I strongly suggest it, because some parts are simplified. So what we have to prove that if Fn is equal to un minus tun, and Fn converges to F, then there exists a U such that F is equal to U minus TU. Okay, so this is the definition of closure. And just as a comment, where the compact plays a role and why the proof in this setting is much easier here. Well, simply because we know that this converge, we know that this guy is compact, so if un is as a bounded norm, well, then we know that up to subsequences it should converge strongly, and then you pass to the limit. So what is the problem now? The problem is that since if the kernel is not 0, then I cannot infer that it's bounded, then this guy is bounded. Okay? So the key point is to show essentially that the UN, that, okay, you have a family of UN satisfying this relation, which can be taken to be with uniformly bounded norm. Okay, so this is the key point. Let me say here, the key point show that one can take norm of UN less than C for all n. Okay, so let's do that. And since I don't want to use this approach where it is much easier, but let's follow the framework book, so what we do? So we want to find, in some sense, what is the minimal norm. So here it means that I want to find the UN with minimal norm. So, but the remark is clearly that if V belongs to the kernel of identity minus T, and then you see where the difficulties arrive, see that I don't do that step, then identity minus T UN plus V is equal to Fn. So I cannot deduce immediately that it's bounded, but I can take the minimal norm. So what I do, and now there is a part we didn't do that, but we can do it now. So let Vn belonging to the kernel of identity minus T be such that so the Un minus Vn, this norm is the minimum, okay, is equal to the distance of UN from the kernel. So why it is Vn exist? It exists because the kernel is finite dimensional. And then finite dimensional spaces are locally compact. So there exists a sequence converging, and well, there exists a sequence converging to the minimum, but the sequence is compact, so it converges in norm also. Okay. So now we are in this relation, and also it holds Fn is equal, so let's call this Wn minus Twn, where Wn is equal to Un minus Vn. So it is essentially in some sense, is the minimal norm of Un. Okay? So let's prove that, so this step is because I'm not using this space. Now I want to show that this Wn now, which it can be seen as a quotient, as a point in the quotient, as norm bounded. So assume that Wn tends to infinity. We divide Fn norm on Wn is equal to, okay, Wn divided by norm of Wn minus T Wn divided by norm of Wn. Okay, so we pass to the limit. So this guy converges to 0 because Fn being converging is bound uniformly. Okay, so we discover, and now we have a sequence. Well, on the other hand, this guy up to subsequences converges to, well, some vector. So let's call this converge to Z because it's compact. And what is the, well, okay, this converges to Z, and then I deduce that this guy converges to Z.
Professor?
Yep.
Why we discover that T Vn over what norm of Vn converges with what? We don't know. Vn, it's unbounded sequence, so we cannot apply compactness of T here.
Where here?
Yeah, next converges to Z.
This one. This is norm 1.
Why?
It's T applied to the ball of radius 1.
Oh,
because
yes,
Wn over norm of Wn
yes,
norm is 1. Yeah, okay? You agree?
Yes, thank you.
Yeah, this, sorry, that's the thing. So I'm saying that, so this is T, you see, it's T applied, so let me say what is this guy here. This is T applied to Wn over norm of Wn, which is a unit vector, and T being compact, I have a subsequence that this object converges, and since this goes to 0, this object converges, this object should converge too. And it converges exactly to the limit. So essentially what I deduce, that 0 is equal to Z minus TZ. So Z belongs to the kernel. However, let's go back. What is the distance of Wn from the kernel? So if you look at the definition, the distance, so this means that Z belongs to the kernel. On the other hand, Z is the limit of Wn, and the distance of Wn from the kernel we look at the proposition here is exactly 1. So I get a contradiction, because then Z, so if I pass to the limit of this object, I get the distance of Z I get from the kernel is equal to 1, because distance is continuous. And so contradiction. And now it's done, because what we know is that then Fn is equal to Wn minus T Wn. And again, this is bounded, so this converge up to subsequences to some, okay, let's say the U. Okay, U has been used to some V. This converge to F. And so this guy should converge to exactly F minus V. And then if this guy converges, I get that this guy converges to F minus V. So Wn converges to some W, and F passed to the limit is equal to W minus TW. So this is the proof of the fact that the range is closed. And if you repeat with this setting, it's much easier because you don't need some steps like this one. Okay, but still you have to prove, however, that the equivalent classes here are represented as a closed subspace of E. Because that's a formal definition, but you need some representation. Okay, so we can go on now. So now we want to prove the second point. So the third point, that if the kernel is 0, then essentially the operator is inverted, is surjective, and vice versa, which is a property which is standard for this case, but is not standard for general operators, as we have seen for the shift. The shift is injective, but is not surjective. So let me take the space I need here. So now we want to prove that if the kernel of identity minus T is only 0, then the range of identity minus T is the whole space. Okay, so this is one direction. Assume, so it is again by contradiction. And why is that so? Because essentially, if it is not the case, then we will show that T is non-compact. So by contradiction. Assume that, okay, the range, so the range is not E. So what it means that range of identity minus T is E1, okay. We know that it's closed containing E. This is a closed subspace, but is strictly contained in E. So this means what? It means that, so now we have that T, so so now what does it mean? It means that T of E1, okay, it cannot be the whole E1, no? Because E is contained, but is not equivalent to E1. Sorry, I have one comment because I see something wrong in my notes. Yeah, okay, this is because, okay, let's look at this guy, and then I have that because tu is equal to, for any u is, okay, let's say u minus tu is in E1, and so if u belongs to E1, I deduce that tu belongs to u plus E1, which is still in E1. Okay? But E1 is closed, so it means that T is a compact operator which maps E1 into itself, so I deduce that T belongs to the compact operator also on E1. Okay. Now, identity minus T E1 is some subspace E2, which is contained in E1, but is not equivalent to E1, because I know that E1 is equal to identity minus T E, and if it is equal to the other, should be identity minus T E1, and then the kernel cannot be 0, no? Because I have that a strictest space is mapped into the same as a larger space. Okay? So then we go on, and then we discover again T of E2 is contained in E2. Which is closed, because I know that the range is closed if it is compact, sorry, is contained in the compact set, and then I have that E2, sorry, oh gosh, I forgot, I was saying it is, and the UT belongs to the compact operator of E2, and then I can repeat, and identity minus T E2 is some space, closed subspace E3, contained but non equivalent to E2. Okay. So if this happens, basically I construct a family of nested closed subspaces, and you see where we are heading to, no? To show that then T cannot be compact. So we can construct sequence of closed nested subspace, well, nested closed subspace okay, defined by, okay, we just iterate, you see, E1 I minus T, E2 is I minus T E1, I minus T E1, and then it is I minus T squared. So En is identity minus T to the N of E. Okay, take, so now we have to build a sequence such that T UN does not converge. So, and the sequence is what? Take UN belonging to En minus En plus 1 such that, okay, here I choose the distance to be distance 1/2. Okay, the norm of UN is equal to 1, and then we know by the Ritz lemma, so this is the Ritz lemma, the distance of un from en plus 1 is greater than 1/2. This is Reed's lemma. Now, let's compute what is the difference. Then, TUN minus TUM. So we estimate now. So you see what's going to happen. Going to happen that this guy, so essentially, so each one, well, if I have identity, I want to use that identity minus t maps one quantity space into the next one in order to show that, well, the distance of this guy should be larger than 1/2. Okay, so this is just algebraic computation. So I write like un minus TUN. So let me do already a triangle inequality. So we spare some space. Sorry, no, this is not the smart thing. Sorry, I did just not the triangle because I need this larger. Un minus TUN plus, so it should be with the minus, plus minus TUM. And what is left is plus un minus um. And now we do the observation. So let's assume that m is less than n. Okay? So this guy belongs to en plus 1. Because his identity minus t applied to un, and un belongs to en. This guy belongs to en plus 1. Because his identity minus t applied to and belongs to em. Okay, so this is equal to, well, is this guy is en, or is greater or equal than the distance. So, well, it's minus and here I have a vector w, which is the sum of this object, which belongs to en plus 1.
Second, third sense, just both of them belongs to en plus 1.
En plus 1.
This one, it belongs to en plus 1. First and third. Sum first and third.
The first is n plus 1. This is n plus 1, and this is en. In any case, since they are nested by this assumption, is n plus 1. Now we go back, so this distance is larger than, this norm is larger than the distance. So it's larger than 1/2. And that's a contradiction, because then the sequence of TUM is not pre-compact. So it's not convergent subsequences. Okay. So now we have this implication. By contradiction, if this is 0, the range is whole. So let's do the opposite implication. So we have to prove that assuming the range of identity minus t is the whole space, then the kernel is only 0. Okay, what we know now, okay, if the range of identity minus t is equal to e, if you remember something we did Tuesday, is so you remember that the range, so the orthogonal of the kernel, so this should be the kernel of identity minus T star orthogonal, the closure, but we know it is closed. So now, if this is the whole space, so the only way the orthogonal is 0, sorry, if this is the whole space, the only vector which is 0 for the whole space is 0. So this implies that the kernel of identity minus T star is 0. Okay, let me, I think maybe recall that. So this means that so the kernel orthogonal are all the U such that f U is equal to 0 for all f in the kernel. And now you observe that since I know that this guy is equal to E, the only f by definition of dual space, which is 0 on the whole vectors, on the whole E is f equal to 0. So this means that f is equal to 0. Is the only one in the kernel. Okay. Now, if you remember, we have also the theorem which tells you that if T is compact, then the adjoint is compact. And we have seen, yes, 2 days ago, and because, why is that so? Because essentially, whenever you want to pass to the limit to the image of this star, is like using the Ascoli-Arzelà theorem on the closure of the image of the ball by the definition of duality. Okay. So now we add the two things, so that this is compact, its kernel is 0, so we deduce that the range of identity minus T star is equal to E star. Now, if you recall, what we have now, we have that another relation we see, we recall that, so what is the range of identity minus T star orthogonal?
Kernel of I minus T.
It's exactly the kernel of identity minus T. But since this is E star, this guy here is equal to 0, and then we deduce the theorem. So we choose point C. So last point, that the dimension of the two kernels are the same. So now we have to prove. So let's prove first an inequality. So we want to prove that D star dimension of the kernel of identity minus T star with obvious notations is less or equal than the dimension of the kernel of identity minus T, which is equal to D. With obvious notation, you define these two numbers. Okay, assume the opposite. Greater than D. Okay, so the idea here is to essentially extend, so the idea, extend T to a compact operator, injective operator, and in order to deduce with not subjective. Not surjective. Okay, so I'm going to contradict point C. Okay, let's see how I do the extension. So, let me make a drawing and then you understand. So if this is E, now I have this one is the kernel of identity minus T, which is dimension D. Now I'm using something I just wrote here. So the range of identity minus T star is the kernel, sorry, I'm using this guy here. So the image of the kernel is equal to the identity minus T star. So let's say this is the range. And it is defined as the orthogonal of a subspace whose dimension is D star. Okay? So the range has a codimension D star. But now D star being larger than D, I have space. So if D star is larger than D, then there exists, let's say, an operator lambda, which maps the kernel of identity minus T into, let's say, any, we don't have a notation, say the codim, say is close the supplementary space, the supplement space, but okay, it's into some, let's say, S, such that, okay, maybe S is not a smart notation, let's say some F, such that, so dimension of F is equal to the star, and then I have the decomposition E is equal to the range, identity minus T plus F, and lambda cannot be surjective, can be injective but not surjective. Injective because, okay, I have enough dimensions, but the dimension is invariant for linear maps if they are invertible. I cannot increase them. So lambda is injective, but not surjective. So the last step you take then, let's say T prime, or S, is equal to T plus, okay, and lambda acts only on this guy, so it's lambda compose the projection of the kernel. And now I observe that the kernel of S is equal to 0, because, well, if this map to 0, since this guy in some sense acts on vectors which are not in the range. So imagine a Hilbert space, I can take really the orthogonal spaces. And so if S is 0, then this guy is 0, or identity minus T is 0, and then this guy should be maps to 0, which is a contradiction because this is injective, and this says that the point is in the kernel. So essentially, I have that the kernel of identity minus S is equal to 0, but the range cannot be the whole set, simply because the image of lambda does not cover the topological supplement of the space, of this space here. And now we precise the thing is contained, so it's different than E. So I have a contradiction with point C. Okay, now we make the things a little bit more precise. So in Hilbert space, I should have done in Hilbert spaces because it's much easier. So in Hilbert space, so let me redo the drawing in the Hilbert space. So in Hilbert space, I have the kernel. Then I have the range. Then the range is the orthogonal of the kernel of this guy, which is now is really the orthogonal. So the range is orthogonal to this one, which is the kernel identity minus t star. And then you observe that the dimension of this guy is less than the dimension of this guy. Okay, take any map, for example, the projection. And you discover that, I have a map which maps the whole space into the range and the subspace of the kernel. And the map is injective, but it's not surjective. So maybe if you want to try with Hilbert space is immediate, because I don't have to do the machinery that now I have to take out. So in the discussion done here, the problem is how to build such a map. So I need to build essentially, okay, let me see how to do this here. Okay, I need to define the projection on the kernel. I need to find the topological supplement, so this orthogonal space F in Hilbert space would be really the orthogonal space. Okay, so first of all, we construct the projection on kernel identity minus t, which has dimension d. Okay, there is a general approach, but here we are very specialized. So now so the projection is not like, it's just a continuous operator. It's different than in Hilbert space. Let's call it projection, but it's a continuous operator. There is no orthogonality in these spaces. So take E1, ED, a base, vector base on kernel identity minus t, so I can replace with any finite dimensional space. The set f tilde, okay, it's equal from, let's say, the kernel into R with the properties f tilde j such that fj xi ei, sorry, is equal to delta ij. And I have it because this is finite dimensional. I don't have anything. Can be really the scalar product. And it is orthogonal in any notion I want. Then extend them to, okay, the norm of this guy I can put equal to 1. So I can say ei equal to fj equal to 1. Extend to fj from E into R, continuous, and then define the projection of X is the sum fjx or fix ei. So it resembles like the projection for Hilbert spaces. Well, here I should assume that the EI are orthonormal, and then I say these are the components. So now I have the I want to show, okay, something will resemble decomposition. Then, what is the topological supplement? If, okay, let's say G is equal to all the U in E, such that F I U is equal to 0 for all I, which are the intersection of the kernel. So these are the points such that their projection is 0. So it's equal to the kernel of Pk. Then I have the projection on G. What is the projection of G of a point? Is X minus the sum is bounded. So the difference with respect to the standard Hilbert space is that I'm not saying that it is a norm, I'm saying that it is bounded. So what I can say here is that, okay, this is expressed sometimes like saying that E is the topological sum of two vector spaces. So E, say in this example we have the kernel, thus, and then we have this space which I call G, and P over the kernel of identity minus T, and P over G are bounded operators. So as a remark, since we are enlarging the subject, not every closed subspace has a topological supplement, so has the properties as above. So there is no projection, continuous projection. And there is a theory which says that if every topological space, if I don't remember badly, has this property, every closed subspace, then it is Hilbert. Okay, so, but we just observe if one is finite dimensional, then yes. So there are even others, but finite dimensional spaces, they have the topological supplement. So they can be written as, so they have a continual projection. Cool. Okay. So now the definition of P on the kernel is done. So now the second part is how to build the space F, which is the topological supplement of this set, which has codimension, D star. Well, we know that, okay, we just use the fact from this thing over, I think I just cancel, of the range of identity minus T is the kernel identity minus T star orthogonal, define. Okay, what means this relation? It means that these points are characterized of being 0 on all the linear functionals in the kernel. And I know that this has dimension D star, so it's equal to, so the orthogonal of some linear span of the span of some linear functional Fi. By definition, it is the star, then it's the span of this guy, and then it's the span of this guy orthogonal. So I discovered that the range is equal to all the u, such that, okay, fi u equal to 0 for all I 1 to d. And then I'm so happy because I define, or take u such that, well, I can say, okay, ui such that what I need is that fi, like I have here, so fi ui, okay, let's say norm of ui, norm of fi to 1, and then I can state this guy to be delta ij. And define, okay, f is the span of this ui, and the projection over f, so the continuous operator, is the same formula that I have here. Sum fi x, x, and the projection over the range, okay, is 1 minus the projection over k. Okay, so this second step gives me the space F. Now, lambda is any linear map from this space to this space F, which is essentially is the lifting of a linear map from Rd to Rd star. Okay? Because the linear map is represented as a linear map on the coordinates here. So let's say I need to change it. So this is F tilde. So it's a linear map from the coordinates here to the coordinates there. But this is y. Okay. So with this long digression, because we didn't cover this part, we need to add here. So this was part B. Let me collect the statement here. So we can construct a continuous projection on the kernel and a map lambda which maps the kernel into this space F, which is equal, well, it's the span of this guy over here. Not that I say these are F tilde, just to be too easy to think. Okay, and then if we go back, I'm happy because now I have all the tools I need for defining operations. So define S is T plus lambda composed P. Okay, P kernel. So it's perfectly defined, T is defined. I project on the kernel and I map the kernel into this space here. Now I say that S is compact. Why is that so? T is compact and lambda is finite rank. So lambda is finite rank, and hence this is compact, is bounded, because this is bounded, and this is okay, is bounded, is a linear operator in finite dimensional spaces. And T is compact, so being a linear subspace of the compact operator are the sum of compact operator is compact. Okay. What are the properties now? Assume that U is equal to S of U, which means U belongs to the kernel identity minus S. Okay, so let me write U is equal to T U plus lambda composed P kernel identity minus T. But now I recall that I have this nice projection on, well, the topological supplement of the range. So projecting on the range, I discovered that the projection on the range of U is equal to, okay, T, the projection on the range. Okay, but the projection of the range of T is, so the projection of the range, because this is 0, so I discovered that the projection of the range of identity minus T U is equal to 0. And this means that this is mapped into 0, because this is already in the range by definition. I discovered that identity minus T U equal to 0, so U is in the kernel. Okay. So now if I look then at the kernel, I get this is 0, and then I have lambda compose now the projection of the kernel is the kernel. It's equal to 0, but lambda is injective. So U equal to 0 because lambda injective. So we discover that the kernel of identity minus S is 0, but by construction, lambda cannot be surjective because this has dimension D and this has dimension D star. And then this is a contradiction. Because I've proven in point C that, okay, if the kernel is 0, then it is invertible. It's a little bit long, I'm sorry, and it's because we did not cover some arguments which are not that important, at least. Okay, now we have to do the opposite. So we know that D star is less or equal than D. And this has been proved because so I want to prove the opposite. Then D star star with obvious notation, so is the dimension of the kernel of the second adjoint, is less or equal than D star. Now we will see that this is implies that they are the same, because so what is this guy here? This is the kernel of identity minus T star star in E star, but this is contained clearly the kernel of identity minus T up to the isometrical embedding, because if I have a vector here which is 0, well, when I do the embedding it's the same. So the T star star coincide with U, with T, so commutes with the isometrical embedding. Okay, and then this implies that T star star is larger than D. So everything go together, D gives the point D. And this is the proof, which is quite long. I'm sorry, but it's very important. Okay, now with this in hand, we do the last part, which is the spectrum. And it's already almost there, because it's something like to study the spectrum of when lambda is equal to 1. You see, is identity minus AX equal to 0. So we keep this theorem, which is needed in the following, and then we discuss the spectrum of a linear operator. So because of the choice of living in a space with vector space on the real numbers, is not the best choice studying spectra, because, well, you know that the right space is a complex. But it should be considered in the complex space. The complex plane should be considered is lambda, and that's why we need some. So now we discuss spectrum of linear operators. So definition. What is the resolvent? The resolvent is which is called rho of T. So are all the lambda, or should be, the correct thing should be complex number. So, but here, since we are in, there is a little bit of ambiguity. I will write complex, because it is the best, and well, we will not be very precise, since we work so far on real vector spaces, and then I take complex number, but I think more or less the extension of many results is trivial. Okay, so such that T of, let's say, lambda identity minus T is invertible. So the spectrum by definition is the complex plane minus the resolvent. So are all the lambda such that, okay, this is not invertible, and since we are working with bounded operators, not being invertible, it means that either the kernel of identity minus T is different than 0, or lambda and is not surjective. And so it may happen that, for example, this is 0, but this is not the whole set. However, for the point of view of eigenvalues, we need that the kernel is not 0 here, so there is a third definition, which is the point spectrum, which are the eigenvalues. And these are the set rho 0, it's called, no? Sigma, okay, there was another, sorry, this is called sigma of T, and this is sigma point T, are all the lambda in C, such that the kernel, so is not injective. So it means that I have an eigenvector. Okay, so now let's start with some properties. Very general properties. So the spectrum rho T, sorry, the resolvent is open, and sigma P, sigma is contained. Okay, if I'm in the complex plane, I should say that in the ball, so all the lambda, nodus lambda less or equal than the norm of T. Otherwise, okay.
And non-empty also.
Pardon?
Spectrum is non-empty for any bounded operator.
The spectrum is non-empty, yes.
It's not trivial fact.
Yeah. Okay. So let's see. Okay, let's see this guy, this inclusion. Okay, so let lambda, I'm sorry, larger than norm of T. Then I want to solve lambda u minus tu equal to v, because I want to show that is invertible. So I need to prove that there exists a unique v. Okay. Now, use this hypothesis. So equivalently, u equal to t over lambda u plus v. Let me say that this is a contraction. Then I leave to you. So the same analysis applies when I want to prove that it is open. So if lambda 0 belongs to the resolvent, then we need to solve lambda 0 plus epsilon lambda tu equal to v. I do the same, so I rewrite like lambda 0 u, lambda 0 minus t u equal to v minus epsilon lambda. Sorry, epsilon lambda u, so epsilon sufficiently small and lambda less or equal than 1, just in a neighborhood. And then by assumption this is invertible. So there exists, this is invertible. Then I obtain that u is equal to lambda 0 minus t v to the minus 1 v minus epsilon lambda 0 minus t u, and then I say that is a contraction less than the norm t to the minus 1, then is a contraction. Okay? Okay. Now, the fact is not empty depends on the fact that the C is algebraic complete. So we will not do that because in our setting on real numbers, this can be clearly empty. So now instead we analyze at the end the operators where the spectrum is real. Okay, so there is an application yet. So the theorem, what about the spectrum of compact operators? So if T is a compact operator and E is infinite dimensional, so 0 belongs to the spectrum of T the spectrum of T minus 0 is, okay, is contained in the point spectrum of T. So only 0 is the one which cannot be an eigenvalue. And the point C is that, okay, sigma T, so the cardinality minus any ball centered, well, a ball in C is 0 epsilon is finite. Okay. So it's much nicer than generic operators where, well, you can put the spectrum almost everywhere, and then you find an operator which has this property. So let's see. So this is quite straightforward. So point A. If, sorry?
It's just it's corollary from the fact that compact operators is ideal of the set of bounded operators. It's ideal. Namely, bounded operator and multiplying compact operator is always compact operator.
Yes. Well, yeah, because, okay, if you want to spoil instead of ideal, it's just that if there exists T to the minus 1, which means that 0 is sorry, 0 is in the resolvent, then T composed T to the minus 1 is equal to the identity, and it's compact because it's the composition.
Yes. And identity also compact, yes.
And then we know that if it is infinite dimensional, it cannot be compact, the identity. Okay, so that it's only in the point spectrum. We'll go back to our properties. So which one we need here? This guy, point C. If I have a point which is non in 0, so let's say lambda, I divide by lambda. So, and the point C says that if lambda is different than 0, then if this is non-zero, this is non-zero, and vice versa. So if this is not E, and if this is 0, this is E, and vice versa. So just point C of Fredholm. So what about point C? Point C is because if you have infinitely, yeah, if you have infinitely many with, let's say, lambda greater than epsilon, then I deduce, essentially, I build a sequence as we did to prove that, for example, this guy is closed. I build a sequence of vectors whose distance is not 1, is larger than 1/2, for example, and the distance of the image larger than 1/2. So let's see the proof. I should have time. I don't know if I can finish today. There's still one part which is more interesting. I think we cannot finish by today, I'm sorry. Okay. So assume let lambda n be a sequence of now we know that it's only point spectrum, so it is of eigenvectors, eigenvalues for lambda n larger than epsilon. Doesn't matter. So now it turns out that I can take En, which is in the kernel. Norm of En equal to 1 in the kernel. So these are eigenvectors. So let En is the span of the first one, and okay, as usual what I do, so I know that En is contained in the previous one, so En is contained but not equivalent to En plus 1, En plus 2, because every time I add a UN or I En, and this En cannot be in the previous one, because if they are in the previous one, they are the composition of previous eigenvectors, and this is not an eigenvector, or it is one of the previous one. You just is a simple computation, which it works exactly as in the finite dimensional case. So now let UN is the same in En minus 1 with the norm of UN equal to 1. You see that the proof is always the same, distance UN En minus 1 larger than 1/2. And now I have to prove that this sequence is a sequence which has no compact subsequences. Okay, so let's do the computation. Okay, I just do the following. TUN over lambda n, TUM over lambda n, which is the same, no? Because I divided by a quantity which is non-constant, but in any case is larger than epsilon. So if this object goes to 0, well, it means, well, sorry, if this object, they converge the lambda, okay, let me say that lambda n also converges to some lambda. So if this object goes to 0, they converge to 0. So if this, if I have the subsequence converges, then this converges. Okay, and then as we did before, I rewrite as the sum of the quantities. So it is T minus lambda n UN over lambda n minus T minus lambda m UM over lambda m. And what is left is UN minus UM. And now the reason is the same. So this object now is 0. Well, it's not 0 in any case. This belongs, sorry, is not 0. So let's say n less than n, just to the. Okay, so this in any case is in a subspace which is in En minus 1. Why? Because the component along En is cancelled because it's in the kernel. This guy clearly is in EM. This guy is in EM. And so I have the distance of UN minus something, which belongs to En minus 1. And this guy is larger than 1/2 by definition. So I have the contradiction.
I think we can improve the statement of the part C. Namely, the eigenvectors also finite. Namely, eigenvectors.
Yes, but yes, because the kernel is finite dimensional, and we can say that the eigenvectors are finite, but the thing is that since I'm not assuming anything about the vectors, is something like in the finite dimensional case where, okay, you can have these generalized eigenvectors. So the number of eigenvectors is less than the dimension of the kernels, and the sum of the dimensional canons is finite because of point A of random alternative. But, okay, yes, but it is like in the finite dimensional case that, well, either you speak of generalized eigenvectors, or you can, I mean, is a subset. They don't span the whole space. Okay, and finally, we can end up with, okay, now, so for compact operators, we know that essentially up to 0, which can be shown in the spectrum, not necessarily in the point spectrum. The resolvent is, sorry, for lambda different 0, we need only the point spectrum. So let me cancel this part now and do the last subject, which is the spectral decomposition of self-adjoint operators. And this is the last one. Okay, so essentially what we need, so the aim of the same as for, okay, symmetric self-adjoint. Here we are really a space, so it's symmetric. If I would have worked in complex space, I should have called self-adjoint matrices. So it means that T is equal to T as star, or equivalently, since we are in a real thing, well, it works. So T, U, V, U, T, V. But now you see that in order to write this guy, I need that T is an operator on a Hilbert space. Otherwise, they act on different spaces, and the notion is meaningless. Okay, so the thing, and we know that if I take the real scalar product, well, also the complex, I know that for matrices, this implies that the eigenvalues are real. So I'm not proving that the eigenvalues are real, because but okay, maybe as an exercise is nice. So let's see what. Pardon?
It was easy proving just one line. Let lambda be eigenvalue and
the spectrum. The eigenvalues is one line because it's like in the one dimension, but in the spectrum.
No, we will prove that any eigenvalue is a real number for self-adjoint operator.
The eigenvalues, yes, but the spectrum, I mean, for compact, okay. For non-compact, well, I need to do something. It's not immediate that you can have that this is 0, but this is not.
Continuous spectrum, maybe.
But yes, at the end it's work because you take the imaginary part and then you see an estimate on what is I mean, you get an estimate on the sequences, and then you pass to the limit. Well, this is one proof, but there are other proofs. But in for this one, I just stay with the book. I don't want to do more. So let's see the proposition here. I don't have time probably because this is quite long. Yes, this is unfortunately quite long, and other two subjects. Okay, let's just do the comment. So, proposition, if T is a linear operator on a Hilbert space and it's self-adjoint, then Okay, the spectrum is real. And actually you have more that the spectrum is contained in an interval which can be computed by M is the minimum, TUU, capital M is the maximum, DUU. The existence is because of the compactness of the weak compactness of the ball. Finally, the norm of T is the max between minus M and M. Okay, let's see how much of the proof we can do, otherwise we will restart. Maybe so you see from the form of the statement that this quadratic form will play the role. And it is a quadratic symmetric form, so it's like a new scalar product. If it is coercive, and whenever I take a lambda outside this interval, I get a coercive quadratic, symmetric quadratic form, so I'm very happy. So define A U V is equal to lambda minus T U V, and then you have that this is symmetric, simply because T is self-adjoint, coercive, and bilinear. So now we need to solve we should need to solve, let's say, that A U V is equal to, okay, we should solve lambda minus identity U equal to, let's say, W, and we know that we can solve AUV equal to WV by Lax-Milgram. The two things are equivalent, no? So, and this shows that, okay, let's say only for the real number. I'm not going to touch the self-adjoint, the fact that is real. So we'll not go this one. Okay, so we have that lambda greater than E is an error solvent. So lambda belongs to the resolvent of T, and the same for lambda less than M, the minimum. Now you take T minus lambda. Okay, so we have the two estimates. Now I want to show that, okay, there is no time. I think we have to stop here. Okay, so the next lecture, which will be Wednesday, we will finish the proof. So we've showed that these two values are actually in the spectrum. And then we will show that if it's not only self-adjoint, but it's compact, we have the decomposition in eigenvalues and eigenvectors, orthogonal eigenvalues and eigenvectors, as in the finite dimensional case. So summing up, the conclusion is that for compact self-adjoint operators, or more generally for compact operators, are the most natural extension of matrices to infinite dimensional space. And there are even other objects that you can construct which resembles objects that you have in linear algebra. Okay, are there questions? Otherwise, I just stop here. So as I said, the next lecture will be Wednesday, because on Monday and Tuesday I have another appointment. Okay, so have a good weekend.
Thank you, Professor.
Thank you.